Okay, it is time. We're going to get started. So last time, we're in chapter 3, and we started with chapter 3 with very simple metal structures. There was things like simple cubic, body-centered cubic, face-centered cubic. And then we got into our very first ceramic structure, and we said ceramic structures are way harder for two main reasons. They can be much more complex. First, because you have two different ions, which means you can have different sized ions, right? You can have something huge and something really small. They could be close to the same size. They could be kind of different, right? And the second difference is that they're going to have charge. And when you have charge, you have to have charge balance, right? So those two things together gives rise to a great deal more complexity, right? And the very first example we gave you was rock salt. This is sometimes called the AX structure type or sodium chloride structure type. And we said that, hey, this looks a lot like two interpenetrating FCC lattices that have been offset by half of a lattice parameter, right? One has the origin right here at that bottom left-hand corner, and one has the origin located half of a lattice parameter in any of the principal directions, right? And if we do that, we end up with the rock salt structure, okay? And the last thing we did is we said, oh, great. We know that the anions and the cations like to be touching. Therefore, we can figure out what the lattice parameter will be, since they're probably going to be touching along that edge length, and it's going to be 2 of our cations plus 2 of our anion radii will give us our lattice parameter. So today we're going to pick up building on that. We're going to talk about a few other crystal structure types, namely the cesium chloride structure, zincblende, perovskite, and a few of the different carbon structures. We'll practice drawing planes and directions, since we need a way that anyone in the world could talk about the exact same plane and direction. We have some formalism that we follow. We'll calculate linear and planar density. We'll talk about how you can stack differently to get different layers forming. And by the end, I hope to actually get to single versus polycrystalline materials and even X-ray diffraction. We probably won't quite get that far, so we'll probably need one more lecture on this. The test will be next Friday. It's pretty soon, but that's because the civil engineers leave after that point, so we have to have 2 exams for them. Well, it'd be nice to give them 2 chances to have 2 exams, right? That's their final exam. So because of that, this homework that I'm going to assign this Wednesday will be the last homework that will be covered on the exam, right? So it'll have stuff from chapter 3 for sure. I'll probably also put some stuff from chapter 4, which is polymers, on there, okay? So that'll be, I'll assign that soon. Okay, so the next crystal structure we're going to talk about is cesium chloride, CSCl. Yeah, Kylie?
Is this exam like cumulative going back if it's like the final exam?
Normally, like the final exam for the end of the semester will definitely be cumulative. This one, it will be mostly on chapters 9, 3, and 4. Everything behind that is fair game, but I'll tell you exactly what to study, and it's going to be 9, 3, and 4. Again, just like before, I'll have a study guide posted by Monday next week. So you have all week to ask questions. And I'll do a review just like usual. So we'll talk more about the test later. Just a heads up that it's coming. Okay, cesium chloride can be thought of as also 2 different interpenetrating lattices, but they're not FCC lattices anymore. Cesium chloride is 2 interpenetrating simple cubic lattices, right? So the red atoms here are red atoms in a simple cubic arrangement. But, the green ones... We could also draw the green ones, right? That there's another atom here and here, right? They form their own simple cubic lattice that would extend in the same way, right? So the question that commonly gets asked is, why is this not BCC? Why is this not body-centered cubic? What do we think? So there's a size issue. The main reason, though, is a body-centered cubic is a metal where all the atoms are the same, right? You could place the origin at the corner and in the center and get the exact same structures. This one you'd get they're different atoms, so it's not the same thing. So that's the main reason. But you're right, that size is the reason why this forms this way. So given that this has a coordination number of what? How many atoms surround the cesium? There's 8 chlorines that surround it. I guess this would actually be chlorine. Either way. It says something about the ratio of the ions relative to what we saw in sodium chloride. In sodium chloride, the ratio was what? It was between this range when you took Rc over Ra, and that corresponded to a coordination number of 6, right? So this one, chlorine's just a little bit larger, right? Chlorine's pretty large, and so you get a larger coordination number. Excuse me, cesium's larger, right? The next structure is zincblende, sometimes called zinc sulfide. In this one, if you take Rc over Ra, the ratio corresponds to a coordination number of 4, right? And it has to be that way for both anions and cations. Why does it have to be the same coordination number for anions and cations there? Why did it have to be the same one for here, right? For both anion and cation. Why couldn't we have coordination number of 8 for cesium, just like the formula predicted, but something less for chlorine? Why do they have to be the same? Maybe turn to your neighbor. Let's get thoughts going. Like, what do you think? Tell your neighbor. Okay, anybody got a guess? Why does it have to be the same? We know why the cation has to have the number that it has, because the Rc over Ra ratio tells us. But why can't the anion have whatever number of neighbors it wants? Why does it have a specific number, and why does it have to be the same? Any thoughts? Ashley, let me pick on you. Any idea? Does anybody have an idea? Who said something? Somebody felt brave. And they don't anymore. What do you think?
If they're interpenetrating the same simple cubic structure, then they have to have the same number in order to continue that structural pattern, wouldn't they?
Yeah, that's a great way to put it. That we know what the structure is, and if it was something different, then you'd have a different structure, right? So that you knew that because we knew the structure ahead of time. What if we didn't know the structure ahead of time? You just calculated the coordination number. How would we know that the coordination number is the same for both? Kylie, got a guess?
Is it just because there's like one cesium per every chloride, basically?
Bingo.
You know the
That's it. The stoichiometry is a 1-to-1 ratio. So that's exactly right. She says, well, we know for every cesium there's a chlorine. So if for every cesium surrounded by 8, the other one has to also be surrounded by 8, right? It has to have the same ratio. For structures where that's not the case, say a 1-to-2, if you calculate what the cation is, and there's twice as many cations, and it's 8, for example, its coordination number, what would you expect for the anion? You'd expect half that many. You'd expect 4, right? So we're going to see some examples of that. So for zincblende, if you look at this structure, here's the zinc surrounded by the yellow sulfurs. There's a lot of open space in this structure. I should have brought the model. This has lots and lots of open space, meaning we could stuff more atoms in there. It's not like we're space constrained, but the stoichiometry is constrained, right? So we don't put additional ions because we have to have that 1-to-1 ratio, okay? So zincblende looks a lot like sodium chloride or the rock salt structure because it's also 2 interpenetrating FCC lattices, right? But this time, instead of being shifted by half of a lattice parameter along either the x, the y, or the z direction, it's shifted by 1/4, 1/4, 1/4, right? So in all 3 of those directions, it's shifted by a quarter, meaning we go 1/4 of a lattice parameter along the A, 1/4 along that direction, and 1/4 along that way. So we have 1 lattice starting here and 1 starting there. But if you look at this closely, you'll see that the gray atoms are also in an FCC arrangement, meaning, you know, it's easy to see it with the yellow. In the yellow, we've got an atom on the corner and an atom on the face, right? Well, in the gray, we've got our atom, that becomes now the corner and that becomes the face, right? So these are both 2 interpenetrating FCC lattices just like before, okay? The difference is that one had coordination number of 6 and this one has coordination numbers of 4. So let's actually try drawing one of these. Let's pick in the z direction, so in the up direction, let's draw 1/4 of the way up this unit cell, and let's draw that plane. What does it look like? So sketch that out with you and your neighbor. If you were to draw this plane, what's it look like? How many atoms are there? It's just the two that we intersected, right? Now if you go up 3/4 up in the direction, what do you have?
Mirror image.
Is it the same thing?
Mirror.
Now they're shifted like that, right? So that's the way to think of this structure, right? Soon we'll have, by the end of class today, we'll have enough tools for us to tell you some arbitrary direction, like along this weird direction. You'll be able to draw that whole plane, and I want you to be able to sketch where the atoms are at. So we'll get some practice doing that later today. Okay, the next are AX2 type structures, like rutile. Rutile is the white paint on the walls. I think we mentioned it before. Titanium dioxide is easily the most common white pigment. It's very cheap. It's all over in the earth. It's really important, right? So this structure and many of the other important ones are not in the book, but they're worth mentioning. Rutile structure, it has a 2 cations to 1 anion ratio. So just like before, if I wanted you to figure out the structure of this thing, I'd have you take RC over RA, and you'd figure out that the ratio corresponds to a coordination number of 6. However, we know that oxygen can't also have 6, because then we'd have TiO. We'd have equal amounts of titanium and oxygen. Here we know that we have to have twice as much titanium, so its coordination number must be 3. And we can see that in the structure. The red atoms are oxygen, and they're surrounded by 3 titanium. This gray atom is the titanium, it's surrounded by 6 oxygens, right? So it gives rise to this sort of, it's called a tetragonal structure. This is the first time we've seen a structure, I guess other than hexagonal, that isn't cubic, meaning this direction here, B, is larger than A, and these two directions are the same, so we'll call them both A. It's still 90-degree angles. It's like a rectangular box, but one side is stretched longer. We call that tetragonal, and we'll come back to that in a few minutes. And then the next type of structure that's really important to know is the perovskite type structure, or ABX structures, meaning now we have 2 different cations and 1 anion, right? So examples are like barium titanate, strontium zirconate, lanthanum aluminate. There's billions of these things. There's tons and tons and tons of combinations that we can have, not billions. There's many. There's thousands, right? And they're technologically extremely important, these materials, right? So the way to think of this structure is you have a very big cation and a very small cation, and then you have the anion, which is also quite large, right? So this structure is extremely flexible because it has different sites where different ions can sit that have different charge or different size. You have the A site, and it is 12 coordinate. We already decided that an atom sitting here has 12 nearest neighbors. If you remember back to FCC, we calculated that. 12 nearest neighbors means that means you can put a really big atom there because it's surrounded by 12 oxygen. So it must be a big atom that goes there. So things like your rare earth, like lanthanum, is going to go there, or barium, which is huge. Strontium's not that huge, but it's bigger, right? Those things are going to go on the A site, right? And then you can fit a really small cation, something with like a 6 coordination number in the middle, right? So that's going to be your titanium 4+, zirconium 4+, aluminum 3+. Those are much smaller, right? So they're going to sit in the middle. And then on the faces, you've got your oxygen, okay? Again, A is oftentimes 2+, and B is oftentimes 4+. All we know is that when you have A, B, O, 3, this is definitely going to add up to -6. So any combination of ions you have here that add up to +6 might be a candidate for the perovskite structure. That can be a 2,4, like it very commonly is, but like lanthanum aluminum, this is +3, and that's +3. There's other ones like lithium tungstate, O3, where this is +5, and that's +1, right? So you can have any combination that adds up to 6 might be a candidate for this structure. Why is this structure so common is because it can fit big and small, right? And atoms are all sorts of different sizes, and the likelihood of having something that's the exact same size for both of those is not as common. It's more common that they're going to differ in size, which might be accommodated by putting the big atom where the orange spots are and the small atom where the black spot is, okay? Now there's ideal and non-ideal perovskites. You can have an ideal perovskite, meaning that this is perfectly cubic, meaning that the anions touch the cations everywhere. That means right here, those two would be touching, right? And also right here, those two would be touching. Well, that will only work if this ratio holds, right? Along this top, we say that that distance is √2 times A over 2, and that must be equal to the radius of the orange atom plus the radius of this gray atom, right? Or in our case, that's the A and the oxygen, right? And then this way, this distance, that's just A over 2, right? So that must be equal to the radius of the oxygen plus the radius of the B atom. So when you rearrange this, and basically say that if the lattice parameter, if there's one single lattice parameter, and it's cubic, right? So it's the same in all those directions. When you divide these things, you get this expression. If you take this expression and solve, if you plug in the radii and you get t equals 1, then you have a perfectly cubic structure. In the real world, perovskites aren't perfectly cubic. They can be stretched out. You could have something like this, right? I'm drawing it super exaggerated, right? But you might have like it stretched in that way, okay? Question? No? Okay. So if t equals 1, then we call it an ideal perovskite. We will come back to this in a few chapters when we talk about piezoelectric materials, because they rely on it switching between a distorted and a cubic state. Okay, the next class of compounds that we're going to briefly talk about are silicates, and we're going to talk about them because they're everywhere. If you grab a handful of dirt, it has a ton of silicon, aluminum, and probably potassium in it, and oxygen for sure, right? So silicon is just everywhere. Silicon and oxygen are the two most abundant elements on the planet. So it's not surprising that so many different compounds, minerals, things we look at, have silicon and oxygen in them. And the basic building block of all silicates is this tetrahedral unit. Remember, a tetrahedra is something that has 1, 2, 3, 4, right? So something in the middle, and it's coordinated by these 4 things. If you took OChem or gen chemistry, tetrahedra are really important because carbon has 4 bonds that want to be equally spaced out, and this is the shape that it often takes to have those things equally spaced out from each other. You might remember that has like 109.5 degrees. Anyways, so that's the tetrahedral shape. So you have your silicon in the middle, and it's surrounded by 4 oxygens. Well, if you do the math, silicon's plus 4, oxygen is minus 2, and there's 4 of them. So that means this unit itself has a minus 4 charge. So it's what's called a polyanion. It's a group of atoms that together is not charge balanced. So for this to form structures, you have to get rid of that charge imbalance. You have to make it balanced, right? So they sort of connect together, kind of like Legos, right? My kid loves to play with Legos, and they can connect together in all sorts of different ways. These silicate tetrahedra can connect together in some different ways, right? So you can have them alone, right? You can have them connected on one corner, like a disilicate. You can make chains of them where they're connected sort of in a line like this, or you can make sheets, right? Or you can make 3-dimensional. That's quartz, right? But it's going to connect in probably one of these different ways. And then to make up for the extra charge, we just stuff in other atoms like calcium, magnesium, aluminum, sodium, for example. And those compensate for the charge neutrality. But the main part of the structure is however these things get put together, right? So when you take a material like clay, kaolinite, right? This is the basis of most clays that you learned about in junior high when you took a pottery class probably. When you take that clay and you get it wet, all of a sudden it's plastic and you can deform it. And when it dries out, it becomes rigid. What you're doing is you have layers of silicates and you have layers of aluminum oxide. So these are like aluminum oxygen octahedra. These are silica tetrahedra in a sort of ring structure. And when you add water, water can go in the gap. When water goes in the gap, it allows these things to slide past one another. So all of a sudden it's plastic. You can make it deform. When that water's gone, these things now bind to each other and they become a little bit more rigid. So adding water, it literally wouldn't work if you didn't have a 2-dimensional layer of silicates, right? So I'm not going to say more than that, just to say that there's a lot more there. If you want to learn more about these, in my ceramics class, we cover it in great detail because they're technologically pretty important. Okay, carbon. Carbon itself has several different what are called allotrophs. Sometimes they use the word polytypes. It's not quite the same thing. Allotroph just means multiple different structures with the same composition, right? So you can have diamond, right? Carbon can be diamond. This structure looks like which of the following that we've discussed thus far? It looks like 2 interpenetrating FCCs, right? But what other structure does it look like? It looks a whole lot like the one that we just sketched. This one, the zinc blend, right? The only catch is that zinc blend had both zinc and sulfur atoms, right? So 2 different atoms, anion and cation. Carbon just has the same. Now, why would it form like this? Well, because we know that carbon is covalent. It wants to share bonds, and it wants to share 4 bonds, right? So every carbon has 1, 2, 3, 4 bonds, right? This one here, 1, 2, 3, 4. Even the ones that don't look like they do, that goes, this is on the front face, this atom right here. So if we had the next cell coming out of the board, you'd see that it also has 4 bonds. So it forms this structure strictly because it wants to have 4 bonds, right? Now because of that, this has a very open structure, lots of empty space in there, very strong directional bonding. Okay, so that's diamond. There's more, we'll come back to diamond later. There's graphite. Again, graphite needs to have 4 bonds, but if you look here, I count 1, 2, 3 bonds. So what's happening here? Where's its extra bond? It could be layered, that's a fair guess, but it's not. There are bonding between the layers, but that's just secondary or van der Waals bonding. It needs to have a fourth covalent bond, so where is it?
It's the pi bond that's perpendicular to the p orbital that form the delocalized pi bond.
Yeah, so the bonds do hybridization, which you would have learned about in Gen Chem. We're not going to dwell on it in this class. Basically, there's some double bonds that are shared throughout the structure. So like here, here, and here. Right? If we put shared bonds there, then this now has 1, 2, 3, 4 bonds. This guy right here has 1, 2, 3, 4 bonds, right? So in every one of these structures, there's these double bonds that are shared throughout it. And in fact, these double bonds can move in what are called resonance. So basically, it could just as easily be located right here, here. Oh, I can't even see that. Sorry. Here, here, and here, right? So there's an extra bond shared in that level. The main point, though, is that bonding is happening in that plane, okay? So graphite versus carbon, what can you tell me about the mechanical properties of graphite versus carbon? Which one's harder?
Graphite versus diamond.
Oh, sorry, graphite versus diamond, excuse me. Diamond's definitely harder. And it should make sense because diamond is a three-dimensional covalently bonded structure, so strong bonds in every direction. This thing has extremely strong bonds in plane, but these planes themselves are just stacked together on top of each other like sheets of paper. So you can slide them past each other because it's just van der Waals bonding or secondary bonding holding them together. Which is why, paper like this is or pencils like this use graphite, right? I can drag the tip of this pencil along and I'm leaving behind graphite behind, right? Because it's very easy for it to shear along these planes, right? In fact, when they discovered graphene, what is graphene? That's this, what you're seeing here. That's graphene. When they discovered it, like it was actually a Nature and Science paper. Those are big, fancy journals that you can, you really try and get into. The people who discovered it took Scotch tape on a chunk of graphite, a big brick of graphite, put some Scotch tape on it, dissolved away the Scotch tape, and now you've got this floating layer of graphene, right? It's called exfoliation. So, anyways, it's led to a whole field where basically people literally have rolls of Scotch tape in their labs and they exfoliate things, right? So graphite is important. Graphene is this buzzword. If you watch the, what do you call it? The Big Bang Theory, they had a whole episode on graphene. Anyways, it's become like a big deal, and there's a lot of talk about what it's going to do to replace semiconductors. And that's because when you get a single layer like this rather than many layers stacked up, it changes the physics of how particles move in it. Basically, electrons can move crazy fast through here. There's something called ballistic conduction. We won't get to any of that in this class. Just noted that if you hear the word graphene, all they're talking about is one layer of graphite. And it's never actually one layer. It's usually a couple layers, right? Next up, you've got buckyballs. This is an interesting thing. Basically, if you take 60 carbon atoms and you put them together with 12 pentagons and 20 hexagons, you can make these sort of soccer ball things, right, of atoms. So they've discovered them. There's a lot of research on them. I don't know if they do anything interesting, so we're not going to say more about that. I don't know if they actually have an application. You'll find people publishing like, hey, it can be used for this. I don't know if anybody's actually using it for that, so we're going to skip it. Carbon nanotubes, on the other hand, are something that are interesting. Carbon nanotubes, if you start with a roll of graphite, right? And what if you took part of this and you rolled it up and then connected it onto itself, right? If you did that, you just created a carbon nanotube, right? That's really basically what it is. Now, again, just like you can have graphene, which is one layer, and it's actually multiple layers usually. Same with carbon nanotubes. They're single-walled carbon nanotubes, meaning it is technically one sheet, or you can have multi-walled carbon nanotubes where it's many sheets. But the idea is that it's folded up onto itself and bonded. So now you've got a tube, right? So what? These are technologically very important. They were hard to make for a long time. Nowadays, we've got it figured out. We can make them. And basically, depending on whether you connect this guy right here with this one right there, or if you connect it with that one. So if you basically tilt it just a little bit when you connect it, you can make these be semiconducting or metallic, right? Which is a pretty cool thing to be able to control just by changing how these things connect together. And again, we won't get into why that is in this class, but they can make those. I'm thinking of you guys as engineers. You can buy these off-the-shelf semiconducting or metallic carbon nanotubes. So are they good for electronic properties? Yeah, you betcha. Are they good for other stuff? Definitely. In fact, the main thing where these things get used overwhelmingly is as a stiffening agent, right? So you take something like epoxy, or a rubber or something. If you want to make it more stiff cheap's not the right word because this stuff isn't cheap, but if you want to add very little density while making it much stiffer, carbon fibers are the way to go, right? And if you want to do even better than carbon fibers, then you do carbon nanotubes. Carbon fibers are just basically much larger chunks of carbon nanotubes. Carbon nanotubes are the smallest sort of things that you're going to be able to get. That's a single tube. These things have diameter something like on 100 nanometers, so very, very small. Their length is typically 1,000 times longer than the diameter. Of course, this is variable. You can make them different ways, but you're talking about very high aspect ratio fibers, right? On a very, very small scale. These things can have just crazy strength. 50 to 200 gigapascals, that is insane strong, right? In fact, it's strong enough, making it the strongest known material in the world, an order of magnitude greater than carbon fiber, and that strength is achieved while having a density of 2 grams per cc. Most polymers are right around there, 1.5 or so. So extremely, extremely lightweight, extremely, extremely strong. But if you're ever going to use this and try and get this 200 gigapascals and you're going to make like a rope out of it, then you have to connect these fibers together, right? And when you connect them together, you're talking about van der Waals bonding. And so you never actually see this strength. You can never have a rope that's a 200 gigapascal rope, because you'd have to have fibers that were as long as your rope. And in reality, we don't know how to make them long enough yet. Maybe that'll change, right? Material science is constantly making cool new materials, but right now they can't make them super, super long. If they could, we'd put Elon Musk out of business, because we could have a space elevator. What's a space elevator? If you put something big out in space, a counterweight, and it's in geosynchronous orbit, meaning it's staying directly above some spot, and if you had a rope connecting Earth to that counterweight, instead of taking off with rockets flying out of space, you could just climb the rope, right? But the problem is the weight of this, any known material, steel cable, wouldn't be strong enough. Its own weight would rip it apart. Carbon nanotubes, technically, that 200 gigapascal number would be strong enough. So we could build things like space elevators. Again, that's not going to happen. It's probably science fiction, because we don't know how to make carbon fibers that are several miles long, right? So if that happens, Elon Musk is out of business, which would be a sad thing. Okay, again, one more time, polymorphs and allotrophs. Polymorphism is when multiple structures exist for a single compound. So ice, H2O, we said that ice, there's 11 different phases, right? We haven't changed the composition. There's just different ways of putting those molecules together in a solid. That would be a polymorph, right? Or a polytype, sometimes they call it. Whereas allotrophy has to be a single element. So water has 2 elements. Carbon is a single element. It has diamond, graphite, carbon nanotubes, buckyballs. It has many different allotrophs, okay? Okay, let's talk about 3D crystal structures. I used to talk about symmetry. We're going to skip it for the sake of time. Basically, crystal structures are all based off of symmetry, right? There are structures like cubic ones, which are extremely symmetric. You can rotate it and keep on getting the same structure. You can spin it, you can reflect it, and you keep getting the same structure. And other things which have very low symmetry. What I want you to know about in this class is that there's 7 different crystal systems that have 14 different bravais lattices, right? So here's the 7 systems, right? And then each one of these shown is one of the 14 bravais lattices, which just means you take a crystal system and you apply some sort of centering option to it, right? So let's start with the simplest one, simple cubic, right? And then we can have volume-centered, sometimes called body-centered. So here's our body-centered cubic. You can't have a base-centered cubic, but you can have a face-centered cubic, right? Now if you take a tetragonal system, I reminded you earlier that A is equal to A here, but that is not equal to B. But the angles are all still 90 degrees, right? And now if you go to orthorhombic, A is not the same as B, and it's not the same as what we're going to call C, right? But it's still 90 degrees, right? You can have monoclinic where all these sides are not equal to each other. You've got A, B, C, and one of these angles is not equal to 90 degrees, right? So you can read these descriptions for yourselves, but it's basically these are the different symmetry ways where you can have unit cells repeat. And there's no other ones than this. That's it, right? If you're going to tile to fill all space, this is all of them. Okay? We'll come back to those because it becomes important when we use X-ray diffraction. So next up is how do we talk about distances, locations, directions, and whatnot in planes, and have it so that if I talk to somebody in Japan, they know exactly what I'm talking about in the crystal structure, right? That we all have something that we all use the same way. There's a few rules. First off, when you're talking about positions, you use round brackets with commas, right? So if I'm talking about 1/2, 1/2, 1/2, then I'm talking about an atom at the dead center position, right, of a structure. It doesn't have to be cubic, right, because this is 1/2 in terms of A, B, and C. If A equals B equals C, then it's cubic, but it doesn't have to be, right? So this is fractional coordinates in terms of what we call the lattice parameters, okay? Now directions, you take the final point and you minus the initial point, and then you got a direction. So let's do an example. if I take a structure, right, some sort of cubic structure, and I say I want the direction that connects this point and that point, what would it be? So to do this, start out with the final point. Let's say it's going this direction. Take the final point and just minus the initial point. So you have to do this, you have to pick an origin. Generally, I pick the one in this back left corner over here, right? So that's 0, 0, 0. And then we've got our x direction, our y direction, and our z direction. So our final point would be what? Would be the points of our final. 0, because it's on this back side. This is our final point up here. So it's 0 in the x direction, 1/2, and 1, right? And then our starting point is what? Right, so now when you subtract these from each other, we end up with, we're going to do it in square brackets when we talk about directions. It's going to be -1, and then we don't do commas, and it's going to be 1/2, 1. Oftentimes they'll take and multiply this by a common factor to get integers. So now we would say -2, 1, 2. And then one last thing that you'll sometimes see is they'll put that minus on top. Okay? Those are equivalent. These, same thing. Okay? That is direction. So it's just final minus initial. Not so bad, okay? There's something called families of directions. Families of directions are things that symmetrically are the same. So if we go to our simple cubic structure, where we've got atoms located at all the corners, there's some directions which are crystallographically the same, meaning this direction right there is technically the same as that direction. Since this structure can be rotated, it's cubic, it's the same, then we need a way to identify families of directions that are the same. So what we do is we use pointed brackets, right? And again, you pick one of these directions, any one of them, like this one would be the 0, 0, 1 direction, that's final minus initial, right? So it'd be 0, 0, 1. And it's understood that when we write it in square brackets, I'm talking about any of these edge lengths, right? Because they're all crystallographically the same. Technically, we need special rules when we do this is all called Miller indices, learning how to write these things. Miller indices has special rules with hexagonal symmetry. I don't know why they do this. I still don't know a good reason for it. Because the right way to think of a hexagon, we said, is this is the smallest unit cell. This thing where this that angle between these is 120 degrees. You could do the exact same as before, but for whatever reason, they convert it from a 3-1 into 4 parameters. And they do that by looking down at the unit cell and picking 3 directions in this plane, A1, A2, A3, and then the 4th one goes straight up, right? So it's easy enough if you have the values for, like, for example, say 0, 0, 1. If you want to convert that to the 4-unit one, there's a couple of very easy formulas to plug it into, and you'll get the 4-parameter one. I don't think I'm going to put this on in my exams. It might be one of the homeworks, but I'm not going to expect you to know it very well. So I don't think that it's very useful. Planes are harder. Planes always give people trouble. Directions are easy, planes are harder. There's some rules we're going to follow. First off, you use round brackets. We're going to use Miller indices. And parallel planes are equivalent to identical indices. Let's come back to that in a minute. Here's the rules. When it comes to labeling or drawing planes, first off, let's do labeling, right? If I give you some weird plane like this one here, right? How did you know that that's the 2, 0, 1 plane? What does that mean, right? So here's the rules. If the plane passes through the origin that you selected, select a new origin or draw an equivalent plane, meaning cutting through the same space. So for example, if I had chosen my origin for whatever dumb reason to be at halfway along that X position, I'm going to have problems. So I need to move it, right? So let's draw it somewhere reasonable, right? So let's say we've got a structure. Oh, sorry, it's all blind. If we're trying to do this plane, right, that one there. If we want to do that plane and we want to label it, I need to pick an origin. I would not pick right here because my plane goes through it. I want to pick something else. So let's pick that back corner. Okay, the next rule is identify where the planes intersect the 3 axes. It intersects the x at 1, the y at 1, and the z at 1, right? So this would be, in our case, 1, 1, 1. And then it says, take reciprocals of these locations in terms of A, B, and C. If there is no intersection, meaning it's parallel, then the intersection when you take it, well, the intersection intersects at infinity. So if you take the reciprocal, it's 0. Let me show you an example of that in a minute. So let's redraw this. Do one where that happens. So we have our structure. Let's talk about this plane over here, right? That plane right there. How would we label it? Maybe actually take a shot at this with your neighbor. Follow these 5 steps and guess what the name of that structure, that plane should be. It's that one on that far left side of the dice. Okay, what plane is this? This plane is the... Any thoughts? Anybody? -1, 0, 0. How do we know that? Right? So pick an origin. We've been picking ones over here and we can't because it goes through them. So we put our origin, say right here. We see where it intersects the x, the y, and z. Oh, actually, the way I drew this, actually, it's wrong. I said that wrong right there. So we see it intersects x, never. It runs parallel to the x-plane. It's never going to intersect it. It's never going to intersect the z because it's running parallel to that. But it's running perpendicular to the y, and it intersects it at -1, right? So far we have 0, it intersects at infinity along the x, -1 on the y, and infinity on the z, right? Now we take the reciprocal of that, we flip all those numbers upside down, and we have 1 over infinity is just equal to 0, right? So 0, -1, 0, right? Or, we put these like that, and you can also write it like that. Same thing. Round brackets means planes. Round brackets with commas means points, right? So we've taken off the commas, so now it's not a point. So this would be the 0, -1, 0 plane, okay? Let's do a harder one. Let's do this one, this 2, 0, 1. So let's pick an origin, maybe on this back corner over there, right? So now where does it intersect along the x, along the y, and along the z directions? It intersects x at 1/2, right? So 1/2, and then it intersects y at never, and z at 1. When we invert that, it's 2, 0, 1, right? So it's the 2, 0, 1 plane, okay? So this makes sense? Can you go backwards? So with a neighbor, try drawing the 3, 3, 1 plane in a cubic system. Okay, anybody want to take a stab at it? You want to come down, draw it? Come on down. So, it's going to be like right there, up there on the C. Right, so this isn't so bad. You just did it in reverse. How did he know to do 1/3? Because he took the reciprocal of this thing, and he said, okay, it's intersecting the x and the y at 1/3, right? So that's at 1/3, that's at 1/3, and that's at 1, okay? So you can go backwards and forward this. You'll see a lot of examples on the homework. We're going to test this. Yeah, question?
Why wouldn't you divide by the common factor of 3 so you have 1, 1, and 1/3?
Great question. You can. And if you do that, you're going to draw an equivalent plane. So earlier up here, we skipped it, but we said parallel planes are equivalent with identical indices. So basically what that means, what's a good way to show that? Let's do it on, let's draw a new crystal and I'll try and describe it. So a new structure. Okay, let's take one plane and let's draw it right there. Right, you guys see that plane? That one? Well, we could have another plane if we start it right here, right? And it would go from, let me change the color. Right? Those are identical planes, right? So we'll talk about that more when we get to X-ray diffraction at the end of this chapter. It becomes really important, actually, that you can consider different ones of those. So basically, to your question, why couldn't you have taken this 3, 3, 1 and, gotten rid of the common denominator, say divide all of them by 3? You'd have gotten a slightly different, you would have drawn a different plane, but it would be crystallographically the same plane. It would be just like this, where it's shifted over by some distance. Does that make sense? Kind of? I think we'll see some examples soon. Anyways, we'll come back to it though. Okay. Okay. Atomic arrangements on planes. So you can have families of planes that have the same atomic arrangement. Just like we could have on the cube, we set along the edge that it's the same direction. We can do the same thing with planes. There's some planes where if you were to actually look at the plane, it looks the same. Right? In a cubic one, we'd say that this edge one over here is the same as the top of that cube or the bottom or any of the 6 sides. So we need a way to describe families of planes, and we do that with curly brackets, right? So let's actually sketch it and see. Let's take a BCC crystal. So we've got atoms at these corners and one in the center in BCC, right? So the 1, 1, 0 plane, where would that be? Well, take the inverse, and we know it's going to intersect Z never, but it's going to intersect the other ones at 1. So if this is our X, it intersects that, and that. So it never intersects the Z, right? So we can actually draw that, what the atom's present there. And in the BCC, we know that it's going to be, if we drew the atoms to scale, it'd look kind of something like that, where they'd be touching along the body diagonal, right? So there are other planes that have this exact same atomic arrangement, right? We could say that the, for example, that this one, that plane there, has the same one. So how would we label that? Well, pick somewhere that's not its origin, say right there, right? And this time we'd say that that plane goes, it intersects the X, again, so this is our X direction. So it intersects X at 1, intersects Y at -1, and intercepts that one never. When you take the inverse, you still just have 1 by 0, right? So this plane is in the same family as this one, which is the 1, 1, 0. Because it looks the same, has the same atomic arrangement, okay? So we need a way to describe those, and we just do it with curly brackets like that. And it's just understand that that represents all planes that have the same arrangement. Yeah?
So, like the planes we drew up on the previous cube, that one, if you rotate the whole thing by 90 degrees, you would get 2 planes that were in the same family, but were not the same plane, correct?
Which one? Are you talking about this one?
No, the other one.
This one. And we rotate it which way then?
90 degrees.
We rotate it like so?
Yeah.
Okay.
Then you have 2 planes that would be in the same family, but not be in the same plane. Is that correct? Assuming
Let's draw it. If I were to rotate it and draw it, so now you'd have an atom, a plane that goes from, it would start here and go to here. Start here and go to here. For example, a plane like that. That would be in the same family of planes. It's not the same plane, it's in the same family.
Yeah.
Yeah. Okay, there's something called linear and planar density, which just, question over there?
So when you talk about families of plane versus families of planes versus an equivalent plane, because earlier you said these 2 planes are equivalent.
Oh, great. Different concept, yeah. What's the best way to describe that? Wait, and we'll come back to that. We'll come back to when we get to X-ray, because it has to do with equivalent planes that are stacked up some distance away from each other. So we're going to come back to that. There's something called linear and planar density. This becomes important later on when we talk about deformation. Being able to calculate which one of these planes is the most stuffed with atoms turns out to be something that's important. So we'll come back to it. Right now we just need to calculate how to do that. And to do that, you take, for linear density, you just count how many atoms are present along a direction. Per unit length, how many atoms are on it. And for planar density, it's how many atoms are centered on a plane, right? So if we go back here, what is our planar density of this structure? Well, it has one atom centered, and then quarter, quarter, quarter. So it has technically 2 atoms, right? 2 atoms per whatever this area is. And this area we know is A times square root of 2 times A, right? So for that one, so for the 110, the planar density would be equal to 2 divided by A times square root of 2A, right? So it's just a number, okay? Linear density, you're just going to count how many atoms are along the direction, okay? In the same way. Okay, next up we have close packed structures and how you can achieve them by packing in different ways. So take a look at just the white circles first. The white circles represent the bottom layer, and we had the tennis balls showing this the other day. From that white layer, if we're going to stack the next layer of tennis balls on top of this, we can choose to go on this triangle up sort of thing, or on this triangle down sort of thing, right? We can choose one or the other. In fact, we can name those sites. Let's name one of them the C site, and we'll name the other one the B site, right? And then the last one where we started, we'll call this the A site. If you take and you stack tennis balls alternating between the A site and the B site, over and over, back and forth, you end up with hexagonal close-packed. If you take it and you go A and then B and then C, you end up with face-centered cubic. So this might be hard to see for some people that that's a cube, but like these are the corners of the cube. So you're looking down like the cube diagonal. You can't see the last one because it's underneath everything, right? That's why these have the exact same packing fraction. It's basically the same thing. You've just shifted it in that last layer by over a little bit, okay? And there's lots of ways that people have done to try and visualize this. Maybe that's useful. Why do we care about stacking and packing fractions? Because a lot of structures that are really complex have an easy-to-see pattern that goes through it. I think that's all I'll say about that. That understanding that packing works and that you're filling the space in between the close packing is a way that common structures are formed. Any questions on this? I'm not going to go into depth on that on the test or anything. Okay, next up we got 5 minutes left, so let's just talk about crystalline versus non-crystalline materials briefly. A crystalline material is something that has to have long-range periodic order. So basically we took our little cubic unit cell, right, and we just repeated it over and over and over and over and over, right? That has some sort of long-range periodic order. Not all materials have that. Glass is the most common one that we know of, that we use all the time, that doesn't have that. Glass, rather than having long-range order, it has short-range order. What do we mean? Is that in glass, you have, if I go back far enough, you have a bunch of these SiO4 units, but they're not in a nice organized way like this. This is something that you could tile to fill all space. This thing. But this is crystalline. This is quartz. Quartz and glass can have the exact same atoms present, but one can be organized like this in a clever arrangement, and the other one is just these things are randomly connected together. If they're randomly connected together, it changes the properties in big ways. So we'll come back to glasses at the very end. Then there's something called single crystals. Single crystals means that the orientation of this is preserved all the way through the object, right? So if this chalk was a single crystal, then I could look at a spot over here on this side, and maybe X, Y, and Z are pointed that way. And clear over here on the other side, it's still the exact same X, Y, and Z. And it's just perfectly continuous all the way through. That's rare and uncommon. It's much more common that when you start making something, let's say you had a bunch of liquid in a container, they start to solidify and form solids, and then these things grow, and eventually they bump into each other, and we had what we called grain boundaries, which maybe there's just slightly different orientations, right? Do you have a question, Kylie?
Yeah, that's what I was wondering. Crystal materials have grains, and that like your grain is just big enough to be considered long grain. We say it's long range, but that's just within the grain. And then you understand that grain's butted up against another one. But yeah, you're right. Technically, it only has that translation symmetry operation inside the grain, however big the grain is. Sometimes these things are huge, right? If you guys watch the Planet Earth video, they go in the Lechuguilla caves in New Mexico, and they have just tremendously big crystals, like bigger than people crystals. If you buy a diamond ring, it should be a single crystal, or you paid too much money for something that's not worth anything, right? Polycrystalline diamond's not worth anything, hardly. But so some things are easy to grow. Actually, Emily, what's the status of our sugar crystals? Are they in your locker still, growing? We should bring those back. Those are single crystals, right? So single crystals, technologically, they're very important because they have different properties than a polycrystalline. And we'll talk about why that is later. And I think we're out of time, so next time we'll jump into diffraction and we'll finish this chapter.